Welcome viewers to the 8th lecture in the open online course Computer Numerical Control of Machine Tools and Processes. So, today we are going to discuss about some devices which are used in CNC systems, for example, tachogenerators, printed circuit motors, encoders, etc. What are we what is the focus of our discussion? These devices are required for the proper execution of control action in CNC machine tools. It can be feedback, it can be the requirement of accuracy of profile geometry of the part which is produced by CNC machining, etc. So, let us start right away. Up till now, we have had a look at this particular control loop for CNC systems in continuous control. Just to remind you, in case of continuous control, the control of velocity and the ratio of the axis velocities is done by the interpolator, and in this case, as you can see from the left hand side of the figure, pulses are coming from the interpolator at a controlled rate to the first to the position down counter to keep account of the movement which is taking place, which is going to take place. So, a definite number of pulses are going to be passed through, and it is then going into the control loop for continuous control. Now, continuous control first of all is taking care of the fact that the particular velocity to be attained is achieved and maintained, say in case of linear interpolation, and also this control loop ensures that the velocity, the steady state velocity, say in linear interpolation, is attained within a very short time. This thing can be achieved by making the time constant of the system of this particular axis, that means all the rotary devices taken together, the time constant, that means the response of this particular system to say a step input like a step voltage to the motor. This response has to be very fast. In order to make this response very fast, a tachogenerator, which is nothing but this is our tachogenerator, which is nothing but a DC motor run as a generator. So, that faster it rotates, proportionately higher voltage is emitted at its output. This is the output side, it is emitting a voltage proportional to its angular velocity. Since it is going to be mounted on the shaft of the prime mover motor, therefore, its angular velocity is equal to the angular velocity of the shaft of the prime mover motor. In this case, this is a say permanent magnet DC motor. So, its emitting a voltage is equal to a constant, say kT, multiplied by the angular velocity omega. So, its main advantages, I mean the main reason for the incorporation of this inner velocity control loop is to reduce the time constant or quicken the response time of this particular axis of motion. Okay. So, this is how the tachogenerator is expected to work. First of all, the input voltage is sent and it is compared by an analog comparator with the feedback voltage which is coming from the tachogenerator, which is basically a DC generator in this case, and it is therefore, it is fed in negative feedback. That means, voltage V is coming and from that voltage V t is subtracted, and the result is amplified, since it is going to be a very small value as it is subtracted. Okay. So, this result is amplified through an amplifier which has a multiplying constant of K E. So, we will basically have V minus V t multiplied by K E, and this is fed into the permanent magnet DC motor. Now, if you refer to the lecture on permanent magnet DC motors, you will notice that in that case we had a particular voltage input to the permanent magnet DC motor, which was V. This V value now gets modified to V minus V t multiplied by K A, and this is given in this next equation. V minus V t multiplied by K A minus back EMF is equal to I R. So, just the input voltage term is modified, and therefore, we can process this particular equation in the same way as that equation. So, this particular algebra I am sure that you can follow once you have the notes of that previous lecture in front of you, and it will ultimately be found that the tau or time constant, which was calculated last time to be r into j by k 1 square, gets modified by a multiplying factor of 1 by 1 plus k A into k t by k 1, which is definitely less than 1. Why? Because it is having something added to 1 in the denominator, which is non-negative. Okay. It is a positive term. So, k A k t by k 1 is positive, and therefore, tau will, when multiplied by this particular factor, will definitely become less. This way, it can be, it is shown mathematically that the incorporation of a tachogenerator tends to reduce the time constant and make the response of the system faster to any external stimulus like a step voltage. However, this is not the only way in which we can address this particular issue. There is another way of looking at it. Let us have a look. So, we just have one multiple choice question here. The tachogenerator, which is a permanent magnet DC motor run as a generator, its output voltage is always constant, dependent on its shaft RPM, sinusoidal, none of the others. So, let us take the first option, constant. Tachogenerator voltage output, is it constant? No, as we discussed, it depends upon its the angular velocity of its shaft. So, its first option is definitely not correct. Dependent on its shaft RPM. Now, what is RPM? Rotations per minute. Rotations per minute is related to angular velocity by the relation 2 pi multiplied by n, n being the RPM, 2 pi multiplied by RPM by 60 is equal to omega. Omega is the angular velocity. Let me write down here. So, if you look at this one, 2 pi RPM by 60 is equal to omega equal to angular velocity. It is a measure of the rate at which you are rotating your shaft. So, if it is proportional to omega, it must be proportional to RPM as well, because all the other terms concerned, they are constants, 2 pi and 60. So, definitely B seems to be correct, but let us also look at the other options, in order to make the final decision. The tachogenerator voltage output is sinusoidal always, definitely not, because it depends upon the angular velocity, and the angular velocity does not have any reason to always be sinusoidal. So, C is also not correct. None of the others. This is also not correct, because we have found that B is definitely correct. So, the answer to this is B. Let us now investigate another aspect by which, another way in which we can address the issue of quick response. If we interrogate this particular term, torque divided by polar moment of inertia, it is similar to the term force by mass. Force by mass from Newton's second law we know is equal to acceleration. So, here this must be torque divided by polar moment of inertia must be angular acceleration. So, if we can make this particular term high, it essentially means that we are making the angular acceleration of the system very high. That means, it can catch up with a particular predetermined value of what you call it velocity very fast. However, there is a danger that it might overshoot, but let us not concern ourselves with the other side. Let us concern ourselves with acceleration at this moment, and therefore, we understand that if T by J can be made high for a particular motor, it is going to have very high acceleration, very fast response. So, the answer to this might be the design of a motor which has very small diameter, which means that the armature radius is going to be extremely small, and in order to increase its power capacity, suppose we make it elongated, just like a long cylinder with high L by D ratio. Now, why are we doing this? Because we want to have a high T by J. Now, how does it help? Torque is proportional to the first power of radius. Okay, it's equal to force into the it's a couple. So, this torque is proportional to the radius. Okay, force into radius, or if you consider a couple, force into diameter. Now, if torque is proportional to the first power, what about the denominator? We have not looked at the denominator up till now. Denominator is J. If we consider m mass, it is going to be proportional to the second power of radius, and if we consider geometrical moment of inertia, it is going to be proportional to the fourth power of radius. So, if we increase radius, then we will expect that this term will become smaller and smaller. So, in the same way, if we decrease the radius as we have done now, we will expect that T by J will definitely increase. So, we should have the basic idea will be to make smaller and smaller diameter motors. Surprisingly, when we investigate the market for such motors where time constant is low due to high acceleration, we will find this sort of a motor also existing, and these are called sometimes printed circuit motors or even pancake motors. What is the basic idea in these printed circuit motors? It is first of all accepted that increase of radius of the armature will bring in higher T, because torque is proportional to the first power of radius, but unfortunately, it will bring a higher value of J. That means, the denominator will also become higher. So, that ultimately this term will become very low, because it is proportional to the second power of radius if you consider mass, okay, m r square. So, that means that we do not gain, but we are doing it. It's actually available, this kind of motor. Why do we do that? The term is actually modified from another point of view. It is argued this way, since force into a distance, which is the radius here, since force into distance is defining T, we are increasing the radius, and at the same time let us increase the force, so that it gets a fair contribution from both the terms present in the denominator, in the numerator. And for the denominator J, let us investigate the other multiplying factors like mass and reduce it sufficiently, so that the combined effect of mass and radius square, that will ultimately be reduced. So, in this particular type of motor, all the terms are modified. Let us see how it is done. For example, force. Force can be increased instead of radial field by magnets in the stator. We are going to have transverse field with very strong ceramic magnets. As you can see, some magnets are kept very close to the armature on both sides of it. The armature has become thin, almost paper thin, okay? And these magnets are creating the field for the ultimate motion of the armature. How is the current flowing? The current is flowing this way out and this way in, and the direction is changing due to these commutators. So, how is the motion being obtained? By, if you apply the left hand rule, you can find that ultimately motion will take place this way, because the field direction is in this direction and the current in this arm is this way and in that arm is that way, and that is why the field is becoming opposite in successive pole pair positions. But what about the force getting increased? So, the force gets increased as the field is stronger, that is very good. But what about reduction of mass? How are we reducing the mass of the armature and the rotor system? First of all, instead of having a bulky armature with huge number of copper coils which are very heavy, copper is used for its low conductivity, high conductivity. So, instead of using copper, we go for a compromise, we go for aluminum, which is much lighter. Okay. So, aluminum wires are stamped on the armature as if the armature were printed circuit board, paper thin, not paper thin, but extremely thin plastic armature is used, just like a printed circuit board. And just like we have stamped circuits on it, we are going to have the armature wires on it made of aluminum. So, that sufficiently reduces the weight of the armature. So, mass comes down in the denominator. Add to it the fact that we have a soft iron core at the center of the armature to make the field perfectly radial, but now there is no radial field to start with. So, there is no question of keeping that soft iron core in the middle, and it is done away with, and therefore, this armature becomes extremely light from all these considerations. So, that ultimately what we have is very high forces multiplied by a very large radius multiplied by a large radius square multiplied by an extremely small value of mass. This combination ultimately gives us a very high T by J ratio, so that we get a sufficiently low time constant from this type of configuration. Now, let us have a look at encoders. Ultimately, we up till now we have had look at encoders, but they were incremental encoders with a single row of holes, and through these holes light was passing. That is, we restricted our discussion to optical encoders, and the principle is same for other encoders as well. So, basically the incremental encoders that we have had a look up till now, they have one problem. The problem is these cannot provide information about the direction of rotation, and they can only provide information about the magnitude of distances covered in incremental mode. That means, just this distance has been covered, whether it's in this direction or that direction, that is whether the rotation of the encoder is clockwise or counterclockwise, no information is available in that way, and also whether the velocity is once again clockwise or counterclockwise, we have no way to check. So, in order to solve this problem, there are encoders available called direction sensing encoders. They can sense the direction, but of course, the way in which this is done, it slightly differs from incremental encoders. We will have a look at that. And there are absolute encoders as well, which can sense direction as well as absolute position with respect to some origin. So, let us have a quick look at these devices. So, when we are having a look at rotary encoders, we need to mention one more thing, that is, a rotary encoder is essentially mounted on the lead screw, and they cannot detect any errors in motion beyond the lead screw. That means, say the tool is say the job is mounted on the table and the job is deflecting sufficiently, there is sufficient deflection on the job when machining is being done. There is no way the encoder can access this information, that is, it can get this information and send it to the machine control unit. No, we do not have any way of checking it. So, there is also the question of backlash which is present between the lead screw and the nut, and this is also not received by the rotary encoder mounted on the lead screw. There can be other types of encoders, linear encoders, but the rotary encoder is the most popular one. So, if backlash is present, we may be able to avoid the problem of backlash interfering with the part geometry accuracy in point to point machining, but in continuous control we simply cannot do with backlash present in the machine feed screws. If there is backlash, the geometry of the part will get affected. So, it has to be eliminated. So, one way to eliminate this backlash is by providing recirculating ball screw nut mechanisms. It looks somewhat like this. The depiction is not very good. This is the screw inside. Instead of directly coupling with the nut, we have balls which are circulating, okay, and rolling in between the screw and the nut, and they ultimately get recirculated to enter the helix once again this way. On the other side, they move up, roll in between, go this way, roll, come out, and again they get recirculated like this. So, that sliding friction is replaced by rolling friction, and if these balls are a little oversized and with preloading, okay, one such nut preloaded against another nut with some actual loading, in that case backlash can be eliminated to a large extent. And it has some other advantages and some disadvantages also. If we use a recirculating ball screw nut mechanism, it helps in reducing sticking friction by replacing sliding friction by rolling friction. What is sticking friction? When we are in a region where there is just in between metal to metal contact and fluid film lubrication, in that region the motion of a member against another engineering part becomes uncertain. That means it might be sticking at some time with the other body, and it might be slipping against the other body at some time. So, that jarring jarring motion takes place with a lot of vibration, and it is supposed to be avoided at all costs. This generally takes place at very low speeds, and if sliding friction can be completely avoided by rolling friction, we can do away with sticking friction. So, the recirculating ball screw can avoid sticking friction by bringing in rolling motion instead of sliding. Further, wear and tear is reduced as there is rolling instead of sliding, and backlash is eliminated as we discussed. But the problem is this system is not self locking. If you push the nut, you will get motion. In ordinary screw nut mechanisms, if you push the nut, no matter how much you push the nut, you cannot set it into motion, or you cannot make the screw rotate. So, some other device has to be there to make sure that it is self locking. And lateral dimensions, the nut becomes larger in diameter, okay, taking up more space, and as you know, space is also expensive nowadays. So, Let's have a quick look at the direction sensing encoder. We have two rows of holes and they have a stagger. That means there's a difference in phase, so that these black portions are the transparent places and these white portions are opaque. So that if we have two light emitting devices with receptors on the other side, we will have pulses coming out with a phase difference from these two. So, if you notice, we have written here x and y. So, if the this encoder, direction sensing encoder rotates in a clockwise direction, that is this way, x pulses will lead the y pulses by half a wave. If, however, it rotates towards the counterclockwise direction, then y pulses, okay, it's rotating this way now. Just a moment. Yeah, in that case, y pulses will precede I should have said, in the clockwise direction the y pulses will lead the x pulses, and in the counterclockwise direction x pulses will lead the y pulses. Now, what do we get out of it? There is a very simple binary circuit with the help of which we can completely separate the pulses depending upon whether it is rotating in a clockwise direction or whether it is rotating in the counterclockwise direction. That means, if it is rotating clockwise, I can make the pulses come out this way and this line will be dead. And on the other hand, if it is rotating in the counterclockwise direction, the pulses will be coming out here and this line will be dead in that case. And we can connect these two up to the two sides of the up down counter. Okay. We will come to that when we discuss at length the continuous control loop with respect to interpolators. So, this is how the direction sensing encoder can sense the direction and change the channel along which the output is to be produced. Absolute encoders, they are generally used where we want to be very sure about the particular position with a particular reference point, and they can also sense direction. They are popular in robot movements, robot joints, where generally the movement is restricted within one rotation. So, how does it work? These black portions are transparent, while white portions are opaque. So, when we have sensors corresponding to 4 of these channels, there are 4 channels here. The outermost channel is the least significant bit and the innermost channel is the most significant bit. So, when it is rotating, the outermost channel goes 1, 0, 1, 0, 1, 0 like that. So, first it reads 0, all of them are 0. So, first it reads 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 0 which is 2, then 0, 0, 1, 1 which is 3, etc. 4, 1, 0, 1, 5, 1, 1, 0, 6. That is good. So, that means ultimately the problem of the encoder is solved? Not really, because whenever you are having these sensors placed at a particular place, if there is more than one change taking place, there might well be a case where there is simultaneous changes taking place, more than one change. There might well be a case where there will be some reading error, which means that while change is taking place in the first channel, say in the second channel there is a slight phase difference, so that the change has not yet taken place, so that it might read it might read at this particular position 1, 0, 1, 1, because the first channel has not yet changed. For say several nanoseconds, it might read 1, 0, 1, 1, because change has taken place here. change is not taking place here, just because these are physical devices and they have their limitations. So, this change takes place a little late, and therefore, it reads 1011, and that is a gross error, because it tells the machine that I have reached actually this position of the encoder at this particular angular line. So, these changes, if they are coming in pairs or more than that, they are going to they might result in reading errors, counting errors, and therefore, we have a system of gray code where we ensure that from one reading to the other there will be only one change. So, that counting errors as such will be completely eliminated. But what do we have here? If we start from here and call this 0, you will never get to understand that this is 0, because suppose a person does not know that we have done this change in order to avoid counting errors. What does he do? So, he has to either refer to a lookup table, or the machine control unit inside has to have some sort of decoding arrangement, so that it knows that okay, this really means 0, this really means 1, so on and so forth. So, gray coded disk solves the problem of counting errors by not allowing more than one change at a particular point in time. Thank you very much.